This is the graph of gold price in gram from 1996 to the current year 2023. The price increased from about 40 ringgit per gram until now it's up to about 300 per gram. And this is the graph of infant mortality rate in Malaysia from about 1960 to current. So where the rate is decreasing. So at 30 years ago, the baby could not survive due various factors such as low medical support, mother malnutrition, and disease at that time. Okay, so what is the trend of these two graphs? Can we predict the future by having the history of the trend? Hi, I'm Dr. Kat. In this lesson, we are going to learn about exponential growth and decay. At the end of the lesson, you will be able to differentiate between exponential growth and decay for exponential functions. Let's go with grow and decay. Alright, so you are given an exponential function in this form. Right, in this form where sorry so where a is a constant and c also constant. Okay, so what's different that is that these two constant will give the characteristic of the grow or decay. All right, so here is sorry, I think I made mistake here. So this graph is y exponential by x. It is from our previous slides. And this is for y exponential minus x. So in this both case, a equal to 1, kan? And then c is equal to, this is plus 1 and this is minus 1. So here you can see the effect of either c, which is positive exponential growth. This is exponential growth. And c is minus 1. This is exponential decay. So grow up as x is increasing. So exponential grow and also exponential decay. So let's look another effect for exponential growth. If you have c equal to 2, c equal to 1, and c equal to 0.5, so if we take all of them a equal to 1, so you can see that c, the value f of c will change the slope of this graph. Okay, the highest slope would be here where c is large compared to this value. Alright, so the c value affect how fast the growth happen. Okay, so if c increase, the growth also increase fast. And then we look into the function, the effect of a, the constant in front of it. So suppose that all of them we fix as c equal to 1. That's mean exponential growth. So when we have a equal to 2, equal to 1, and equal to 0.5, you can see that actually the exponential, the rate of the growth same. Only that they start at different value. Okay, so this the effect of a will make the exponentially grow start at different value. That's mean, okay, so that is the effect of a and also the effect of c. We move to the exponential doubling principle. All right, so suppose that we have y as a function of time equal to a exponential ct. That means here we have exponential growth. Okay, the graph is exponential growth. Okay, and then we have some point. We pick at any point of the graph. We pick one point p at time t and at the value of n. So we have this point. Alright, so suppose that this value double after certain time. Okay, that means it's double to 2.2n. That means double at some later time t, capital letter T. So this point would be t plus capital T. Okay, so that we can recognize this point where the value of the n double, so we can have this coordinate. Alright, so this is the function. So the value of y double at certain time t. So we can write it as y equal to y is the argument of letter. That means this is equation, this is a point q, this is point q, this is equal to 2a exponential ct. That means the value doubles, right? The value doubles. Or we can write in another form where y at this point is equal to a, because this is a, c, and then we include t is equal to t plus t. And then from the property of natural logarithmic in the previous lesson, we can separate the ct plus ct, and then we can separate them. Alright, so we can have two forms. So equation 1 and equation 2, they are the same, equal. So we equalize them so that we can cut this ct and this ct, so that we a also we can cut. Then we left with 2 equal to ect. Then also from the previous property, we can have also ct, right, exponential 1, right, exponential 1. Or we can have just ln 2, okay, and then ct, right, ln 2 equal to ct. Then we can have the, finally we rearrange, then we get t equal to ln 2 over c. Okay, that means this t, so this t is equal to ln 2 over c. Okay, so then we get this principle. The function, this function doubles in every interval of t. So for example, here we have this graph, this exponential graph. Okay, this exponential graph, y equal to a exponential ct. Okay, that means the value n, okay, at this point it doubles, so it will get twice in power in time t. And then 2n will double to 4n in the same period of time, and it double 4 to 8, and then from 8 to 16. So you see the double, in the same time of interval t, okay, in the same t, the value doubles. Okay, and it is equal to ln 2 over c. So this c, the interval or length or time depends on the value of c. Okay, then we go to the exponential decay. For the exponential decay, we have here x minus delta minus c, because c is a negative value, so it will decay over time. Okay, for example, here we get time. Alright, so similar to the previous growth. Okay, so in decay, the value decrease by half. So 1 become half, and then half become quarter, and divide, so we had 1/8. Okay, so that's mean it happened in the same interval of time. Okay, this is the time. So in the same interval of time, it become half. Alright, so the interval is also equal to ln 2 over c. Okay, same as a growth. Okay, we can calculate the t, the value of t. So for exponential decay, this t is called half-life, where it is the time taken for quantity to be half of its original. Okay, for example, if we go to the snapshot in textbook 5, Form 5 Physics KPM 2020, there is a decay of the sample radioactive. So from n to half of it in the 1 half life. So after 2 half-life, it become quarter. Okay, and different isotopes decay at different rates, and these rates depends on C. Okay, because this depends on C here. Okay, they have the same different. So different isotope will have different half-life. So that means uranium, sodium, they have different half-life. So long half-life will have lower decay rate. Okay, so here, so this is lower decay rate, this is higher decay rate. It's fast to decay, right? So let's go back to our teaser in the initial slide. Okay, so here from the graph of the gold price, we can actually model it as an exponential growth. At certain point, for example, let's take at 2005 here, the price is 50 ringgit. So after 6 years here, after 6 years, it become 100 ringgit. Okay, the price double to 100. And at another 6 years, so it becomes, this is 200 ringgit. So that means we can predict what happened in the another 6 years. So how much it will get. For infant mortality rate, for example, in 1960, so it is 6.6%. So after 18 years, it becomes 3.3. So that means another 18 years, what will happen? So it will reduce by half. So we can have a better medical support and better mortality rate. We are approaching 0. Alright, so that's all for this lesson. In the next lesson, we are going to the geometric series. Okay, bye.